Ja, zunächst möchte ich mal sagen, dass es einfach eine sehr interessante Veranstaltung war, um überhaupt mal verschiedene Eindrücke, Einblicke von unterschiedlichen Unternehmen zu bekommen, die mit eben Wasserstoff irgendwie involviert sind. Ich persönlich habe jetzt aus der Veranstaltung mitgenommen, dass es für Wasserstoff gerade im Zugverkehr eben durchaus eben Einsatzmöglichkeiten gibt, aber es immer von den Randbedingungen abhängt, ob eben Wasserstoff sozusagen eine geeignete Anwendung findet oder eben nicht. Thank you so much, Nikolaus, for this introduction. Warm welcome to all participants, also from my side. And yeah, my name is Max Weber. I'm research associate within HyCentA Austria in Graz. And before I will talk to you about scientific comparison of drivetrains in the rail sector, I would like to introduce you to the HyCentA. It's a non-universitary research organization at Graz University, which employs more than 90 researchers of different academic background. And our hydrogen competence involves all steps along the value chain, from production to distribution and application of green hydrogen. So, as I mentioned, my presentation is about a comparison of different propulsion systems in the railway. This was especially necessary because the former decision on the hydrogen trains faced major headwind again last year. So we carried out a huge comparison of different technologies and compared these. So why we need to decarbonize is all clear to us. So I don't spend much time on that. Even when the rail sector takes only a small percentage of the carbon emissions, only 58% of the European rail network is electrified. And in light of becoming climate neutral by 2050, these emissions need to be cut down to zero. So the challenge, especially for regional railway, is that electrification via catenary lines is cost intensive and resource intensive. So it's not always the case to use. So this is especially for regional railways the case, because always or sometimes the driving frequencies or the passenger volumes aren't right for using a classic electric train. So here we are. We have some other technologies like the battery train or the hydrogen train, which are suitable alternatives in this. But we need a case-by-case decision on which propulsion systems need to be used, because it always depends on the boundary conditions, which is the best or the optimum technology. So our goal was to build a methodological toolchain for scientific, technology neutral and holistic comparison of drivetrains. and the methodology is based on the following. First, we performed a longitudinal dynamic simulation for all the different propulsion systems to calculate the energy demand based on certain vehicle-related parameters and certain track-related parameters. Second, we collected a large amount of profound data from literature, manufacturers, and experts to quantify, for example, resources, costs, emissions, etc., etc. And for the typical operating period of 30 years for trains, we considered the single life cycle phases of both the vehicles and the infrastructure that is needed to supply the trains with the energy required. And the last one is the multiple criteria decision analysis, which is needed to compare these technologies based on the quantifications from step 2 with regard to several aspects. In this case, it was an ecological aspect, an economic aspect, and also technical and operational aspect. So, as we all know, and I said it before, it's dependent on the boundary conditions. So we need further information about, here in this example, the Zillertalbahn. And I summarized all the track and vehicle parameters on this slide we used for our analysis. And of course, we also need some specifications of the different trains we considered. So I will show all the different trains now. And here you can see, for example, we applied efficiency ranges, the simulated vehicle consumptions, and as the assumed fleet size that is required to operate to maintain the specified timetable. So you can see here, for example, for the battery train, we considered a fleet size that has 1 unit more than, for example, the other ones, because of the timetable. Yeah, and with all these data we just collected, we can have some results, for example, on the CO2 emissions. And as you can see here, we have not only examined the different technologies, but also different energy sources, such as fossil diesel and renewable diesel or e-fuel, electricity from the energy mix and from renewables, and from hydrogen we considered fossil and renewable hydrogen that is produced centralized and is distributed to the application. And on top of that, we also included hydrogen that is produced in a decentralized way via electrolysis. And also there we considered the energy mix or renewables as their energy source. You can see here the results, basic results is the bar, and the both ends of the whisker indicate the upper and the lower limit we just found in literature to describe the technologies. The results include direct as well as indirect emissions from resource use and energy use over the complete lifetime. And what can we observe? So the operation is the main source of emission in case of we use fossil fuels or energy mix. But when we use renewables, the production should not be ignored in terms of the emissions. So as a takeaway, maybe in the medium to long term, only the use of renewables is suitable and sensible for rail operation. A similar illustration is given here with regard to the costs, but I will skip that partly because I will focus on the final comparison. I will show you on the next slide. So we want to analytical evaluate the drivetrains with the multiple criteria analysis, and for this we just used a priority matrix or matrices to give a weighting of the different aspects we used in our comparison. So for example, for the ecological aspect, we not only focused on the CO2 emissions, but also on the particulate emissions or the area amount. Of course, in case of the economic aspect, it's the operational costs and the capital costs. In terms of the technical aspect, it is, for example, the powertrain mass, the powertrain volume, the constructional effort, the technological maturity, and maybe the durability of all the components. And last but not least, for the operational aspect, we considered, for example, the driving range, the maximum driving range the technology is able to, the recharging and the refueling time that is able, and yeah, by this we got a diagram that is shown here, which shows the four aspects in each corner, and also here in this diagram we focused on the diesel from fossil diesel, the electric and battery train using renewable electricity, and the hydrogen train using renewable hydrogen produced via electrolysis on site. So as you can see here, for example, the hydrogen train has its benefits, especially in the ecological, in the economic situation. Sorry, not the economic, in the operational aspect, but has its disadvantages in the economic aspect, for example. So, and now when we will use a really final comparison, we need to compare the ecological, economic, technical, and operational aspect. So we use another priority matrix to do so, and this is one example of result we can get from this. So you can see here the electric train is the best in this case, followed by the hydrogen train, and followed by the battery electric train. So to conclude my presentation, I'd like to highlight once more that there is no universal optimal solution for every case. But some important general findings from the analysis are future powertrains should be based on electric machines. Classic electric trains are the best option in most cases, but battery or hydrogen electric trains are suitable, especially for regional railway if the boundary conditions are fitting. But the suitability of each technology depends on the respective boundary conditions, which is why the proposed comparison should be always applied for each rail project. So, thank you very much.